All right, there we go. Good morning, everyone. My name is Alex Rasmussen, and today I'm going to talk to you about TritonSort, which is our record-shattering, large-scale data processing and sorting system. This is joint work with my colleagues at UCSD, University of California, Riverside, and the Vienna University of Technology. So the amount of data that both companies and large research institutions have to process has grown tremendously in the last few years. And the tasks that we have to perform over these large data volumes are characterized mainly by their extremely high I/O and storage requirements. So some examples of this, companies like Google and Facebook do really large-scale processing over web and social graphs. Companies like Amazon do things like click log and purchase analysis to recommend new products to their customers. And in the sciences, there's been a lot of work on processing enormous data volumes like the human genome. So these large-scale tasks have motivated the development of a number of data-intensive scalable computing, or disk systems, over the last few years, just to handle tasks of this scale. Some of the most famous ones are MapReduce, which Google wrote, its open-source equivalent, Hadoop, and Microsoft's Dryad. Now, these systems scale extremely well. We know of clusters of MapReduce with more than 10,000 nodes in them. And they have really good performance at scale. So for example, in 2009, Yahoo broke the world record in general purpose sorting with about 3,500 machines running Hadoop. And they were able to sort 100 terabytes of data in a little bit under 3 hours. So these results are pretty impressive. Unfortunately, what they mask is some pretty bad performance if you look at a node-by-node basis. So you take that same 2009 sort record run, and if you drill down into individual nodes, it turns out that you're only transferring about 3 megabytes a second off of each of your machines, which is far less than even a single standard hard drive can support. So we're not just picking on Hadoop here. This is not isolated to them. There's a great paper that appeared in SIGOPS last year called Efficiency Matters that highlights a bunch of different systems with this same problem. Now, the traditional approach to overcoming this bad per node efficiency that these systems have is to just add more and more and more machines until you have enough to get the job done. And what this really ends up with is you have these enormous, expensive, power-hungry mega data centers that we keep building everywhere. And so we ask the question, wouldn't it be nice if you could take the per node efficiency of these systems and increase them, say, from 3 megabytes per second per node to even something like 30. Right? Well, if you could do that, then one of two things would happen. Right? Either you would be able to do the same task in the same amount of time with a tenth of the machines, or you could get 10 times the throughput out of the cluster that you already have. So that would be pretty exciting. So the overarching goals of TritonSort is to build a really, really efficient data-intensive scalable computing system that improves the performance on a per-node level versus existing approaches by an order of magnitude. And we're going to do that primarily by building a hardware and software architecture that are as balanced as we possibly can make them, and I'll describe what I mean by that in a couple of slides. Now, some secondary considerations that we're looking at here. We wanted to focus on only using off-the-shelf hardware, so we're not going to build anything custom for this. We're focusing on these large data workloads that I described in the previous slides. But we're focusing on instances of those problems that are so large that you couldn't even hope to fit them in the RAM that you have in your cluster. So you're going to have to go to disk, which makes the problem a lot harder. And as a sort of an initial attempt at this, we focused on sorting. But since then, we have done a little bit of generalization, which I'll talk about at the end. So for the rest of the talk, first I'm going to define a little bit more crisply what I mean by hardware and software balance. Once I've done that, I'll go a little bit into TritonSort's design, and I'm going to pay particular attention here to places where we had to make some trade-offs in order to keep the system balanced. After that, I'll look at TritonSort's performance with particular emphasis on large-scale sorting as a case study. So when I say balanced systems, what exactly do I mean? Well, I'm not the first one to define this term by any means. But for the purposes of this talk, I'm going to define balanced hardware as a hardware architecture where you can drive every piece of that architecture at as close to 100% utilization as possible. Now, what this means from a practical perspective is that if I remove resources from any one of my hardware components, I decrease my size of my RAM, let's say, or I make my disks slower, that's going to slow me down. Now, the choice of a balanced hardware platform, of course, is extremely workload specific. And it's also limited to a great degree by the kinds of hardware you can actually buy. So for example, I might want to buy a processor with 13 cores in it, but I'm only going to be able to buy an 8-core processor or a 16-core processor. I don't really have any in between. Now, having defined what I mean by balanced hardware, I'm going to define balanced software as a software architecture that when you plop it down on top of a balanced hardware architecture, it makes that hardware go as fast as it possibly can. So in 2009, we were fortunate enough to get a grant from the NSF to do scalable energy-efficient data center research. As part of that, we wanted to look at what kinds of problems I/O-heavy workloads were experiencing in the data center setting. And so when we were building our hardware platform, we decided to balance that platform for I/O-heavy workloads. Now, I should emphasize that we did not build this platform specifically with sorting in mind. So the way that we went about selecting what hardware we were going to use for this thing was we started out by saying, well, we have some additional research that we're doing that requires that we have 10 gigabit NICs. So let's do the math and figure out how many disks we can drive at full speed before the network starts to saturate us. Turns out that number comes out to about 16. Now, that decision was fairly cut and dried. It was just a division. The rest of it was a little bit more fuzzy. So we had the choice between buying machines with 4 cores or machines with 8 cores. We decided to go with 8 cores just because we figured that we might need that extra CPU power. As I'll show later, we didn't really need it as much as we thought. Also, when we initially built the cluster out, we built each of the machines with 12 gigs of RAM. We knew that we needed a lot of RAM to do a lot of buffering in front of disks. We found out later that even 12 gigs of RAM wasn't enough for our purposes since we had so many disks that we were buffering in front of. And again, I'll explain more details about that later. So the resulting platform was the UCSD seed testbed. We have 52 nodes. Each of them has an 8-core processor, 24 gigs of RAM, 16 hard drives that are just commodity hard drives, and a 10 gig NIC. And these machines are all connected together with a single Cisco Nexus 5020 switch that Cisco was kind enough to loan us for these purposes. So now that I've talked a little bit about our hardware platform, I'd like to talk at a high level about our software architecture. So at its core, TritonSort is a staged, pipeline-oriented data flow system. So your program that you write in these sorts of systems is expressed as a directed graph of stages. Each one of these stages can be implemented by a number of worker threads, which is controllable by you. And data gets manipulated through this thing by being passed between stages in in-memory buffers. And so when we built TritonSort as a platform, we built it to be really easy to experiment with. In particular, we made it really easy to do things like change the implementation of a particular stage, change how many buffers, in-memory buffers we have and how big they are, change the number of worker threads that each stage uses to execute its particular task, and also control things like CPU and memory allocation for each of those stages. So we built a sorting system on top of this core architecture, and you might wonder, why did we pick sorting? Well, number one, sorting as a problem is relatively easy to describe. It's something that I think everybody has seen from an intro algorithms course at least once. But at the same time, it also has a great deal of industrial applicability. Many large-scale data processing tasks basically come down to a large-scale sort with some data processing on the records in the middle. And another thing that makes this a great way to test disk workloads is that sorting requires that you use all of your disks and your network and your CPU all at the same time for the duration of the run. And so it really kind of pushes the limit of what you can do with these sorts of systems. Now, TritonSort in particular is a 2-phase external sort. Since we have a lot more data to sort than we have memory in the cluster, we're required fundamentally to write and read the data at least twice. We're going to read and write it exactly twice. One of the things that's going to come up throughout this talk is the particular attention that we paid to keeping the system balanced by making the disks stay going at as high as a speed as we could make them go. And the main way that we accomplish this is by making sure that we seek as little as we possibly can. Now, to that end, we decided that we were never going to read and write to the same disk at the same time. And as part of, so to do that, we essentially took these 16 disks that we have on each machine and we partitioned them into two halves. We have an input half and an output half. Now, TritonSort's processing proceeds in two steps. In the first step, you take all of the tuples in your input data set, you read them off disk, and you determine what partition of the final output they belong in. And you transfer each tuple to its appropriate destination partition. We're going to call these partitions logical disks for the purposes of the talk. They're just on-disk files that live on physical disks throughout the cluster. And each one of these logical disks contains, abstractly, a disjoint segment of the key space that your tuples can occupy. Now, at the end of this first phase, everybody hits a distributed barrier, and you have all of your data has been partitioned into the appropriate bucket, but all of your buckets are unsorted. So in the second phase, you have to take all of your buckets, read them off of disk, sort them, and write them back. So at the end of the day, you have a bunch of sorted partitions, which, if you were to concatenate them together in the proper sequence, would give you a sorted permutation of your input sequence. So now I'd like to talk at kind of a 20,000-foot level about TritonSort's architecture. So the whole process starts with input tuples being read off of disk into buffers. Each tuple in these buffers is then hashed to determine which node it's supposed to go to. We've colored those based on node here. The tuples are then copied into a number of buffers, one per destination node. When one of these buffers gets full, it gets sent to the appropriate destination. Now, when you receive a buffer of tuples from another node, you have to figure out which of these logical disks it's supposed to go onto. So you hash each tuple again to determine which logical disk it's supposed to go into. Based on that hash, you append these tuples onto one of a number of linked lists, one per logical disk. Now, when these linked lists get long enough, and I'll describe more about how that works in a second, they get compressed into a single contiguous memory region, which makes it a lot easier for us to write them to disk. And then they're written synchronously to the appropriate physical disk. So now I'd like to go into more of each of these stages in a little bit more detail. So in order to keep the system balanced by our definition, we need to keep the reader, or all the disks, reading at full speed. And so the reader stage is designed to do that. In order to get as much bandwidth as we can, we'd like all these disks to go at 100 megabytes a second. The good news here is that we're not really doing any computation. We're just waiting for I/O and copying data into RAM. And so we don't really need these worker threads to take up a lot of space on the CPU. So we instantiate one worker thread per disk in this stage, and we multiplex them all onto a single CPU core. So that frees up a lot more space for more computationally intensive things that I'll describe in a second. So the next stage, the node distributor stage, so-called because it distributes tuples to nodes, really just does a hash per tuple and scans through the buffer one tuple at a time and does a lot of memory copies. So this stage is really, really fast. We can process data at about 300 megabytes per second per worker thread. So we only really need about 3 threads doing this task to keep the readers saturated and thus to keep the system balanced overall. Now, the sender and the receiver stages, which are responsible for sending and receiving tuples to and from destination nodes, those are a lot more tricky, mainly because you have 800 megabytes per second of data coming in from your readers, and that equates to about 6.4 gigabits per second. And that's all-to-all traffic, because you expect that your tuples are going to be pretty much uniformly scattered across all the nodes in your cluster. And the whole goal of this pair of stages is to keep everything downstream busy. So what you never want to have happen is that your receiver stage, which is receiving data from nodes, runs out of data to receive and has to wait for more data. Because then you're going to get essentially a bubble in your pipeline. And pipeline bubbles are bad because they slow you down. Now, as anybody who has ever written a web server will tell you, it is really not a good idea to have a thread per connection in a situation like this because it really doesn't scale well. At first, we decided, well, is it really going to be that important? Let's just implement it with a thread per connection and see how bad it does. And turns out pretty bad. So we ended up re-implementing this to have all of our destination nodes multiplexed onto a single thread, which just does a tight loop of non-blocking sends. Now, the important thing to note here is that we don't use interfaces like select and epoll, mainly because we expect, if the system is balanced, that you're going to have data that needs to go everywhere all the time. So to emphasize just how bad a thread per connection really does, the red line in this graph denotes how slow we can go in terms of sending before the network becomes our bottleneck and the system becomes imbalanced. You'll notice here that with a thread per connection, you can go up to about 16 nodes and still be OK. Once you get above that, though, you really start suffering, whereas the single-threaded implementation with non-blocking sends does fine, at least up to the scales that we were dealing with in this paper. Now, once you've actually got a buffer full of tuples from another node, you have to figure out what partition, what logical disk they're supposed to go to. And the logical disk distributor stage is responsible for that. So what you do here is you hash each tuple to determine what logical disk it's supposed to go to. And as you do that, you copy each tuple into one of a number of small buffers, which we're going to call logical disk buffers, or LD buffers for short. And when one of these buffers gets full, it's going to get appended onto a chain of tiny buffers. And when this chain gets long enough, and again, I'll describe what I mean by long enough in a second, that gets passed to the next stage to be copied into that contiguous memory chunk I talked about before. So you might ask, why tiny buffers and chains? Well, it turns out that even if you can assume, as we did, that your key space, or that your tuples are uniformly distributed through some key space, and hence that all of your logical disks are going to fill at a roughly uniform rate, you're still going to see a lot of burstiness with respect to destination logical disks at short timescales. If you use large buffers to store tuples that you're managing in this way, what often happens is that you have a tuple that's destined for logical disk X, and logical disk X's buffers are all full. But some other logical disk Y is sitting around with partially full buffers, and you can't move on until after you've copied that tuple for logical disk X, so you have to wait. Now, the solution to this problem is essentially to make it really easy for you to use all of your buffer memory all the time, and that's what these tiny buffers are for. So since we use these really small buffers, on average, they're either empty or they're full. They're never really anywhere in between. And the nice thing about sticking these buffers together into chains is that it allows you a great deal of dynamism with how your memory is allocated to different buffers for different partitions over time. Now, as I've said, once you get this chain passed to the next stage, it gets copied together into a single contiguous memory region. We tried using things like the write vsys call here to make all these chains copied without doing this extra memory copy, but it was really slow. So a thing that comes up here is that when you're talking about these chains, the longer your chain is, the better you are. Well, why? Because if you have a longer chain, you have more data to write to that partition before you have to move on to writing data to another partition. The more data you write before moving from one partition to the next, the less time you spend seeking between those partitions. And hence, the faster your disks go when you do writes. Now, the problem here is that if you want longer chains, you need more memory. And we're already using a lot of memory for these LD buffers, and we really wanted to ask ourselves, well, how much memory do we really need for these? How big should these chains actually be? So to figure that out, we ran a little micro benchmark where we wrote to a bunch of files in round-robin order, and we varied the size of the writes that we did before we moved from one file to the next. Now, you'll notice here at the extreme right side of the graph, which is kind of what we're dealing with, that as you decrease the size of your write, not only does your throughput decrease substantially in the mean, but you also get an incredibly high amount of variance. And for us, variance kills you, because variance causes upstream stages to kind of hiccup and stall. So we ended up, based on this experiment, coming up with a size of about 10 megabytes being kind of the target size that we really wanted to write to. We also enforced the fact that none of the chains that we pass to a subsequent stage is smaller than 5 megs. because we figure that 5 megs is probably as low as you want to go. So compared to phase 1's architecture, phase 2's architecture is kind of boring. You've got a bunch of these logical disks, and you need to read them off of disk and sort them. So you read this logical disk off of memory into a single contiguous memory region, which you then sort and write back to disk. So for the purposes of our evaluation, we're going to look at the sort benchmark challenge. This is a challenge that was started in the 1980s by Jim Gray and is now run by a collection of volunteers from industry and industrial research. They have a lot of different categories in this competition. The one that we're going to be focusing in on particular for this talk is the 100 terabyte sort named GraySort in Jim's honor, and the Indy variant of that sort, which means that we can assume that all of the tuples that we're sorting are the same size. They have a 10-byte key and a 90-byte value. We can also assume that the keys are distributed uniformly throughout the key space. I'm not going to talk about what we can do to handle non-uniformity in either of these cases, but we do have a solution for that. Feel free to ask me about that afterwards. So the first thing we wanted to ask was, well, we wanted a balanced software architecture. How balanced are we actually, right? Well, in both phases, the stage that writes data to disk is our bottleneck stage. This is what we wanted, right? Because we figured that writing to the disk was going to be the slowest thing we were going to do. Now, in terms of the amount of overhead, in terms of throughput that the other stages in the pipeline have relative to these bottlenecks, in general, it's not really all that much higher, with the exception of the coalescer stage, which, since it's doing a memory copy, is absurdly fast. We could have gotten by with one of these, but we just decided to do 8 because it was essentially free, and we forgot to set the right configuration value. Now if you look at, so when I defined a balanced hardware system, I said that we wanted to drive all of our resources at as close to 100% as possible. You'll notice here that we're doing really good at that with memory. We're not doing so great with CPU. It turns out, as I said before, that when we decided on 8 CPU cores, we didn't really need that many, it turns out. For network utilization, I mean, we're going at the speed of the disks, essentially. And so since we have a 10 gig NIC, we have some overhead to play with. One thing that's really important to note is that even though we're seeking in phase 1, we're still going at about 82% of the sequential write throughput of the disks that we observed in practice, which we think is a pretty impressive result. So everything is connected to a single switch, so that makes our problem significantly easier from a scalability perspective. Up to the capacity of the switch, though, we're scaling really, really well. I mean, we couldn't have asked for much better numbers than this. We're currently investigating how this scalability number looks as we move beyond 52 ports. So where TritonSort really shines and where we feel our hypothesis is most clearly validated is in its raw performance. So as of the publication of the paper, TritonSort could go at 0.916 terabytes a minute on a 100 terabyte sort. We fixed a tiny bug in the writer last week and got that number up to 0.938 terabytes a minute. That's an improvement of a factor of 6 in per node efficiency over the previous record holder. So we're pretty pleased with that. Now, once we had this system in place and it was going really fast, we decided to examine what the effect of changing some of the hardware in our cluster would be on the system's balance, because we wanted to convince ourselves that the system wasn't stupendously finely tuned for our particular test bed. So the first thing we did here was we replaced a couple of the nodes' disks with 15,000 RPM drives. Now that increased their speed dramatically. It also decreased their capacity, so we had to lower the number of logical disks that each one of these drives stored. You can notice here that decreasing the number of logical disks has a much greater effect on performance than increasing the disk RPMs, mainly because it moves the bottleneck stage from the write stage to something that's CPU bound. And you might go, oh, you're CPU bound? Oh, God. But we actually have a solution for this. We just didn't have time to describe it in the paper. We also tried seeing, well, you know, we kept thinking, God, we could really use more RAM. We can always use more RAM. Let's try doubling the RAM in a couple of machines and see how much better we do. Well, it turns out that, yes, bigger RAM allows you to write bigger chains. But we're so close to the sequential performance of the disks anyway that it turns out that increasing that chain length doesn't really buy you all that much in terms of raw performance because what you're increasing isn't the bottleneck resource. So this is kind of further validation of the fact that we feel like our hardware architecture is pretty well balanced. So running short on time, but I'd briefly like to talk about our future work. We have a MapReduce implementation that's about 80% equivalent with TritonSort in terms of architecture, and it's really, really fast. I can't really talk about it right now due to time, but I'd love to talk about it offline. We're pretty proud of it. We're also we're trying to consider a bunch of other applications and programming paradigms. I really welcome your suggestions on this. We also spent a lot of time tuning the system in terms of buffer counts, thread counts, buffer sizes, et cetera. We would really like to make the system do that itself to the degree that it can. So that's what we're working on. With that, I will take any questions. Thank you for your time.
Hi, I'm Siddhartha Sen from Princeton University. So I'm intrigued by this notion of a balanced hardware system that you devised. I noticed in the beginning that it seemed like you balanced the parameters pairwise. And so I guess my first question is, would there be, at the onset, maybe a better way to simultaneously balance these parameters? And I guess the second part is, it seems like you may have measured this already, but is there a nice way, once you've deployed your system and you're running your workload, to efficiently tweak the parameters, like disable cores or gradually reduce memory so you can bring the system to that perfect balance?
Okay, so to answer your first question, there's actually another research effort that one of the authors on this paper is leading that is designed to kind of, you drop a workload on a machine and it will tell you what the balanced hardware architecture is for that machine. So
wow. Okay.
So you should talk to Harsha about that. To answer your second question, there are ways of adjusting things like CPU allocation. We don't have an automatic system to do that yet, but we're working on it.
Okay, thanks.
With Badam Princeton, I really like your work. So you mentioned about not having any benefits in increasing the amount of DRAM, but have you tried looking the other way? I mean, what's the minimum amount of DRAM do you need to actually sustain these sort of?
Well, so I think what it comes down to is the less RAM we have, the shorter those chains are at the logical disk distributor. And so for 12 gigs of RAM, instead of our average write size being something like 10 to 12 megabytes, which is what it is now, it would be something more like 5 to 7, which from our results decreases throughput by quite a bit. And it also, as I said before, it really hurts you in terms of variance more than anything else. So, however, if you had fewer disks, right, then you could essentially rebalance the architecture for a given number of disks that you could have, like that 12 gigs of RAM would work really well for. I hope that answers your question. Thank you.
Hi, Steve Hand, University of Cambridge. I liked your talk. You started off by saying you were in energy efficiency. I'm just curious, have you actually measured what the performance you get per watt joule something is? As
a matter of fact, we have. So there's a category in the sort benchmark that is essentially how much can you sort for a joule. They just opened up the 100 terabyte category for that, so we're entering our numbers in both of that, and it's, George, is it like 18 kilojoule or 18,000 records per joule? 9,000 records per joule? Yeah. So and at a terabyte, it's like 8,500 records per joule, which is, I think, like a factor of 2.5 better than the previous thing. So we're actually doing pretty well energy efficiency wise, just because we get just a stupid amount of speed out of this thing.
Thanks.
Mike Friedman, Princeton. I was wondering, do you have any notice of how heterogeneous your disk throughput was in your measured system?
So, it was a lot less heterogeneous than we thought it was going to be, honestly. In general, we see about a 10% difference in terms of the slowest speed to the fastest speed on our disks.
Let me follow up really that.
Sure.
If you the Google arguments about MapReduce. In fact, there's an interesting upcoming paper at HotOS this year about even new disk drives, faster ones, actually differ a lot more than previous generations. I was wondering how your system would behave if actually there's a larger. It seems like you relied on a lot of homogeneity.
Well, I think that we rely on homogeneity to a degree. I think that the buffering that we're doing in front of the disks is dynamic enough that if there were some variance, that the system would auto-adjust for that. We are noticing, though, as we get to larger and larger disk drive populations, especially if we're dealing with drives that are varying manufacturers and so forth, that we are starting to see some higher levels of variance there. what we're thinking of doing is essentially profiling the disks as a pre-step and passing that information into the hash function to essentially redistribute data based on those observed latencies.
Thanks.
No problem.
Two quick questions. We're running short of time.
Yeah, sorry about that, guys.
Arkady Konevsky from VMware.
Hi.
I have a quick question. So this, building the specialized, hardware and software just for one problem is great. You can optimize a lot of things. But if this, as in many cases, sorting is just a small piece of the bigger puzzle, how would you connect the pieces if, after the sorting you would like to, search for something or then later on do something else? How would you,
Sure.
put the pieces together?
So the short answer is we built MapReduce, and we think we can build other things. I'm sorry for being so short, but I guess we're running short on time. The longer answer is we feel like certain components of the system, especially the logical disk distributor, would be fine with anything in front or behind them that are doing kind of whatever you want. And that the key contributions here are both the high amount of disk density that we have in these nodes to achieve balance and also this really, really careful buffer management. So I feel like we could take those lessons and apply them to any one of a number of different systems. Thank you.
Matej Zaharia from Berkeley. So this is cool work, and throughout the talk I was thinking about how to apply this in a system like Hadoop. And the one optimization that I thought it wasn't clear you could do is the one where each disk is only being used for reading or for writing, but never for both. And I'm just wondering how much impact that has overall.
Well, that's a good question. We've never actually tried both reading and writing to the disks at the same time. I think that the key thing that we're trying to do here is reduce the number of times that you seek. And it's a lot harder to predict that when you have multiple threads doing different workloads to the same disk at the same time. It would be a very interesting thing to look at to see whether we could make the disks behave as though they were only being read or written to at the same time from, say, a kernel perspective, without actually doing that. But again, I have no idea what that would do in terms of performance.
Okay,
I have a feeling it would make performance go down, but I don't know by how much.
Yeah. Okay, thanks.
Thanks.
Okay. Thanks a lot.